actual fail, and you look at the percentage bugs and, the number, and you could get open versus resolved, and, you can always add more bells and whistles, but it increases the complexity of the chart. Excuse me. Okay, so, everything goes fine, everything goes normally. I mean, you don't have a whole lot, you don't need much more than that. You're ticking along, everything's pretty nominal. Okay, we're looking good. But when things start to go poorly, when you start to have variance from the plan, that's the point where people are going to start asking questions. Why is this happening? So you need to be ready to bring some test logs and some causal analysis and some other data. Now, this is always a thing to be careful about when you add more data to what you're reporting to people, because every time you add a new set of data that you're going to report to people, you have created an opportunity to confuse them. You don't want to confuse them. You want to enlighten them, right? The opposite of confusion. So, make sure that you explain these charts that you've added meticulously. Make sure people understand them. And if you think people are going to ask questions about it, try to anticipate those and answer the questions either in the chart itself, redesign the chart so that it's self-explanatory, or at the very least have those questions anticipated, be ready to answer them in the first or second or third meeting even when you use them. And remember, bad news always provokes a stronger reaction than good news. So, the worse the news is, the stronger the reaction is, which means the more you will be called upon to have your ducks in a row. There's a saying of success is 1,000 fathers and failure is an orphan. Basically, when you start talking about when things are going bad, people start to question that because they don't want to be the father of the failure in many ways, or the mother. Okay, well, let's suppose we got to do some analysis. We're going to talk about why things are happening. Now, one of the charts that we might use for that is the closure period chart. Some of you have heard me talk about test management metrics before, heard me talk about this. Okay, so closure period, it's kind of a complicated chart in its appearance, but it's actually conceptually, at the detail level, very easy, at least data by data. Basically, you got bug reports that have been closed. So the closure period is how long it took from initial discovery to ultimate resolution of that bug report. So I take the data on which it was closed, I subtract the data on which it was opened, and that's the closure period. Now, I can do two things with that, and I am doing two things with that in this chart. One thing I could do is graph the rolling closure period. Now, the rolling closure period, I add up the closure periods for all the bugs that were closed on and before a given date, and I divide it by the number of bugs that had been closed as of that date. So that's the average across that set of bugs that have been closed to that point, how long it takes to close them. Now, as I go along, like this guy here, this next one includes all of the bugs that were closed in the first little data point there, plus any bugs that were closed since then. Right, so it's a cumulative kind of thing. It's adding more and more data to that rolling closure period over time, which explains why at first it appears to have some level of volatility, but then later it really starts to kind of settle into a pattern. It becomes more and more difficult to budget. Budget meaning move it, not budget like money. It becomes more and more difficult to move it from where it settled because there's more and more data in the average. The daily closure period is different. The daily closure period, I take all the bugs that were closed on that date. I add up the closure periods for all those bugs, divide it by the number of bugs closed on that date. That's the daily closure period. Now, this chart looks pretty good because what's happened is that the rolling closure period is stabilized. It's stabilized at 9 days. And if you get weekly releases in your test operation, that's actually probably not a bad number because it takes about 5 days on average apparently to fix a bug, and then there's another 4 days of lag introduced by that weekly release process. So it's not bad. And the dailies are just kind of bouncing around above and below. It's really looking pretty random here. So process appears to be in pretty good shape. Now, if we'd seen that there were a whole big bunch of daily closure periods other here up at the top, none of them down at the bottom underneath the rolling closure period, that this was all void of any daily closure periods, that would mean that it started to take longer and longer to close bugs, and we'll see an example of that a little later. That's an indicator of problems. Okay, now, breakdown. Where are bugs? There is a principle of testing called bug clustering. And bug clustering says that bugs are not evenly and randomly distributed across the code, but rather they tend to exist in clusters. That is, you tend to find a lot of them in some places and not many in others. Pardon me, there's some water there. So this means that we need to know where these bug clusters are, especially if you're doing risk-based testing. You want to know where are the bug clusters. So this chart is a way to do that, to find the bug clusters, and this is called a Pareto chart. And somebody pointed out today that there's an entry on Pareto, who Pareto was and so forth, on Wikipedia if you're curious. But anyway, the Pareto chart is something that was invented by a fellow named J.M. Juran, who's a statistical process control guru. Juran became interested in something that Pareto, the economist, had written, that is basically the 80-20 rule, this pattern of 80% of the outcomes being associated with 20% of the causes. And Juran wanted to have a way of identifying those 20% of the causes that led to 80% of the outcomes, which is what he called the vital few, and separating those from the trivial many, which are the other 80% of the causes that account for only 20% of the outcomes. Because if you wanted to, say, go after the bug clusters and rapidly increase the quality, or dramatically increase the quality of the system, then that's you would go after where the bug cluster was. You wouldn't go after other areas, and you need to know where the bug clusters are. So this chart, this Pareto chart, will allow you to do it. So what does this say to us? Well, this says that for this hypothetical application, we got 39 bugs in the user interface. That accounts for 35% of the bugs. Then we got another 34 bugs in the edit engine. And cumulatively, user interface and edit engine account for 66% of the bugs. I think it's 34 plus 39. Now, edit engine by itself accounts for 66 minus 35, which is 31% of the bugs. So that's kind of a nice little trick there. You can always figure out what percentage are associated with a single cause by subtracting the percentage immediately to the left. And this is a fairly typical, it's not quite 80%, but what we see here is a pretty clean divide. We have the vital few on the left-hand side and the trivial many. If we wanted to crush the bug clusters in this system, we need to focus on user interface and the edit engine. Okay, now, some of you might be familiar with this phrase control chart from statistical process control, but that's not what I'm talking about here. What I'm talking about is the charts that you use to control testing, low-level, detailed charts. Back in my earlier days as a tester, I would occasionally make the mistake of using these control charts as a way of reporting test results, but tend to see that the information density really overwhelms and confuses your viewers. And another problem here is that it's all data, but there's no trend analysis. You don't see it in the context of time. You don't see any sort of causal analysis, like why is this happening. So I would be careful about using these kinds of charts in reporting. Let me show you a couple examples that say probably dangerous from a reporting point of view, useful from a test management point of view. All right, so you take a look at this guy. This is, whoa, wow, that's a tremendous amount of data, and indeed it is. We have all of our test cases listed here, or at least a substantial